true projects. In this video, we are going to explain about the project entitled as Functional Data Analysis for Prediction of Employee Presence. So, before getting into the video, let me give you the brief description about the project. In today's evolving work environment, understanding and forecasting employee attendance has become essential for improving productivity, resource planning, and smart workplace management. This project explores how functional data analysis can transform traditional attendance records into powerful continuous patterns, helping organizations make more accurate and efficient prediction. Coming to the abstract states that predicting employee presence plays a crucial role in workforce planning, resource allocation, and improving overall organization efficiency. But most traditional prediction models only look at attendance as separate, disconnected points in time. This approach misses the continuous and dynamic patterns that exist in real employee behavior. In this project, we introduce the use of functional data analysis or FDA to predict employee presence more accurately. Instead of treating attendance as isolated data points, FDA converts daily or weekly attendance into smooth continuous function. This allows us to capture deeper patterns such as trends, periodic routines, and unusual behavior. We use advanced techniques like functional principal component analysis, functional regression, and smoothing splines to extract meaningful insights from these attendance curves. With these functional predictors, we built models that forecast employee presence with higher precision compared to traditional methods. Coming to the existing system, in the existing system, the prediction of employee presence mainly depends on traditional statistical or rule-based methods. These approaches rely on discrete attendance records such as daily sign-in and sign-out times. Because the data is treated as separate points, these models fail to capture how attendance actually changes throughout the day. Most of the time, simple time series techniques or basic regression models are used, and they depend heavily on manual created features. As a result, important details like daily working rhythms, fluctuations within the day, or long-term behavioral patterns are often lost due to data aggregation. This makes it difficult for traditional methods to handle complex or irregular attendance trends, which leads to lower prediction accuracy. On top of that, these systems require a lot of manual work for data cleaning, feature preparation, and interpretation, making them less efficient and less adaptability to modern dynamic work environments. All these limitations clearly show that the need for a more advanced and flexible approach, such as functional data analysis, which can represent attendance as smooth continuous function to improve prediction quality. Coming to the proposed system or base paper work. In the proposed system, we introduced a powerful functional data analysis or FDA based framework to predict employee presence more accurately. Instead of looking at attendance as disconnected sign in and sign out records, this system transformed raw attendance logs into smooth continuous curves that represent daily or weekly presence pattern. Using techniques like smoothing splines and functional principal component analysis, the model captures the deep insights such as trends, seasonal behaviors, and individual variations that traditional methods often miss. These functional curves are then fed into functional regression models, which use the shape and flow of the attendance behavior to predict future employee presence with much higher precision. Because the system preserves the full temporal structures of the data, it can detect suitable changes or irregular patterns that would otherwise go unnoticed. The entire process is data driven, requires minimal manual feature engineering, and scales easily for larger organizations. Overall, this proposed system improves prediction accuracy, strengthens workforce planning, and provides organization with a more advanced and reliable tool for understanding employee attendance behavior. Coming to the dataset, in this project we used a processed dataset named df underscore venues underscore process.csv, which contains refined information about different venues or workspaces inside a smart workplace environment. This dataset is created from raw sensor data or access logs and has already gone through several pre-processing steps such as cleaning, filtering, and smoothing. Each entry in this dataset represents a specific venue along with its time-based presence or occupancy details. The key attributes includes the venue ID, which uniquely identifies each workspace, timestamps that indicates when the data was stored, and occupancy or presence indicators, which may come from sensors like motion detectors, RFID logs, or Wi-Fi connection counts. Since it is a process dataset, missing values and noisy readings have been handled, and many features are aggregated to represent daily or hourly presence pattern more clearly. This dataset is essential for the project because it provides continuous structured time series information that can be converted into functional data, allowing us to model occupancy trends, analyzing employee movements across venue, and ultimately improve the accuracy of employee presence prediction in smart workplace management system. Coming to the novelty or extension or enhancement or improvement. As an extension, we developed additional advanced models to further improve prediction accuracy and enhance the overall robustness of the system. This includes a convolutional neural network model and an ensemble voting regressor that combines the strengths of XGBoost, gradient boosting, and k-nearest neighbors. Among this model, the DFMM approach delivered a strong performance with MAPE of 4.69% and R-square of 91.3%, while the voting regressor achieved a MAPE of 6.05 with an R-square of 93.1%, demonstrating excellent generalization capability. To improve interpretability, we further integrated explainable AI techniques such as LIME and SHAP, which helped identifying the most influential features contributing to the prediction outcomes. Additionally, a user-friendly Flask-based web interface was developed, enabling users to upload input data and generate real-time predictions using the trained models, thereby offering an interactive and seamless experience. Coming to the flow of the work, firstly, we need to import the packages. Essential Python libraries such as NumPy, Pandas, Matplotlib, Scikit-learn, TensorFlow, and stat models are imported. These packages support data pre-processing, visualization, modeling, evaluation, and deployment. Next, we have exploring the data set. The dataset is loaded and inspected to understand its structure, attributes, data type, and basic statistics. This step helps identifying patterns, inconsistencies, and the overall distribution of employee presence across the time. Then we have data pre-processing. In data pre-processing, we need to remove the null values and also remove the duplicates. Then data visualization. Graphs are generated to visualize how employee presence varies across days of the week, highlighting trends such as peak and low attendance date. And a heat map is created to understand relationship between variables and identify which attribute most influence prediction. Then splitting the dataset. The dataset is divided into 80% of training and 20% for testing, allowing the models to learn from past data and be evaluated on unseen samples for generalization. Next, building the models. Multiple models are developed to compare performance and select the best predictor. Then, training the models. Each model is trained on the processed dataset, learning attendance patterns, trends, and functional curves to predict future employee presence. Next, comparison of the models. All models are evaluated using multiple error metrics and information criteria. This ensures a comprehensive performance comparison across accuracy, generalization, and model complexity. Then we have comparison graph. Visual comparison graphs are generated to easily observe which model performed best based on scores across all evaluation metrics. Then save the best trained model. The top performing model is saved for deployment. This allows real-time prediction without retraining. Then explainable AI visualizations. LIME and SHAP are used to interpret how each feature influences the prediction. This adds transparency, helping users understand why the model predicts certain presence values. Coming to the front end, a Flask-based web interface is created with user authentication, supported by an SQLite database. This ensures secure access to prediction features. The interface collects required input data for analysis and forecasting. User uploads a CSV file containing presence-related parameters along with the desired prediction duration. The uploaded data is clean, formatted, and transformed to match the model's expected input structure. The best saved model process the user provided data and generates accurate employee presence forecasting. Predicted results are presented to the user through the web interface in a clear and interactive format. The algorithms used are AdaBoost, SARA Max, LSTM, FTSA, DFMM, RobFTS, CNN, and a voting regressor. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, back-end is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. To execute this project, firstly, we need to open the code folder which contains the project source code files. This project code folder is a complete package of your project's code base containing everything needed to deploy, test, and develop your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contains the algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is the database file used to store the user information. Now, coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. By using the command cd followed by a space, paste the path which you have copied. This command is used to change the current directory to the code folder path. Then, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with a port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front end built using the Flask framework. In this page, we have home button and sign in button. Now click on sign up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, contact number, and a password. Then click on create an account so that all the given details are stored in signup.db and the login HTML will be opened, where we need to access the application by username and password. Then click on sign in. The prediction page has been displayed. In this, we have home button, graph button, notebook button, and sign out button. So firstly, we need to click on home button so that the batch employee presence prediction will be opened, where you need to upload your employee data to generate accurate presence forecasting using the advanced AI analytics. So here, this is a place where you need to drop your employees' data. Here we have how the application works. Firstly, we need to upload the CSV or Excel file. Then AI will analyze the historical patterns then receives weekly forecast, so that finally the exploring the results will be planned. Whatever the file you're going to upload here, the file requirements are like data, temperature, precipitation, total reservation. The file, whatever you applied, the file requirements must consider all this. So firstly, let me give the inputs. The inputs are given from the test case of the code folder. This is a sample.csv file which we need to upload here. And then here we have number of weeks to forecast. Here we can give any number of weeks, like it may be 6, 7, 8 or 10 or 40. The range will be like 1 to 52 weeks. So firstly, I'm just giving 8 weeks. Then we click on generate forecast. So the given input is pre-processed and the forecasting results are displayed. So we have given 8 weeks. Here the predicted employee presence for next 8 weeks has been displayed. Week 1, Monday, Tuesday, Wednesday, Thursday and Friday. Like in the same way, we have for 8 weeks. And we also have go back to home and view data analysis or explore the notebook. So here we need to click on view data analysis. When you click on this, the graphical representations of the models will be displayed. So firstly, we have the graph of weekly number of people per day. This graph illustrates the number of people present each day from Monday to Friday across 6 different weeks. In general, most weeks shows higher attendance in the middle of the week, with Tuesday, Wednesday and Thursday consistently reaching the highest numbers, often between 600 and 700 people. Monday usually begins with moderately high attendance except for week 1, which starts significantly lower than the others. By Friday, all week shows a noticeable drop, making it the lowest attendance day across the board. Each week follows a similar pattern, rising from Monday to a midweek, then declining towards the end of the week. This suggests that activity or participation trends to build early in the week, reaches its maximum around midweek, and then decreases as the week concludes. And next we have daily number of people and reservation over time graph. This graph shows the daily number of people and total reservations over time from late 2022 to late 2023, highlighting strong day-to-day fluctuations in both metrics. The number of people consistently remain high than the number of reservations, often ranging from 400 to 800, with occasional peaks about 900 and some sharp drops. They may indicate closure or lower activity days. Reservations generally fall between 100 and 350 and follow a similar fluctuating pattern, suggesting that varies regularly throughout the year. Overall, the graph illustrates a dynamic pattern of activity with both attendance and reservations rising and falling frequently rather than following a smooth long-term trends. Next, we have correlation matrix. This correlation matrix shows how 4 variables like number of people, temperature, precipitation, and total reservations related to each other. The strong relationship between the number of people and total reservations with a high positive correlation of 0.84, meaning that when reservation increase, the number of people tends to increase as well. Temperature and precipitation have very weak correlations with the number of people, like minus 0.08 and minus 0.04, suggesting that weather conditions have little direct effect on attendance. Temperature and precipitation themselves shows small positive correlation of 0.20, indicating that slightly warming days may also have more precipitation through the relationship in a week. Overall, the chart shows that reservations are the main factors linked with attendance, while weather variables have minimal impact. And next we have forecast evaluation optimized voting regressor graph. This graph compares the actual numbers of people, indicating blue line, with the predicted values from an optimized voting regressor model, represents red dashed lines. Each point allows the x-axis represent an index in the dataset, while the y-axis shows the number of people. Overall, the predicted values closely follow the actual values, capturing the major peaks and drops throughout the series. Although there are small deviations, especially around sharp increasing or decreases, the model consistently mirrors the overall patterns, indicating strong predictive performance. The close alignment between two lines suggests that the model is effectively at forecasting attendance based on the input features. And next, we have the comparison graphs. These graphs compare several forecasting models of AdaBoost, SARI Max, FTSA, LSTM, DFMM, CNN, voting regressor, and ROBFTS across multiple performance metrics. The top row shows accuracy metrics like MAE, MAPE, and RMSE, where the lower value indicates the better performance. Here, the voting regressor ROBFTS, CNN, and FTSA generally achieves lower errors, while SARIMAX performs the worst. The R-square plot shows how well each model explains the data, with DFMM, voting regressor, ROBFTS, and CNN achieving the highest scores. The bottom rows displayed information criteria metrics like AIC, BIC, AICC, and HQIC, where lower values indicates efficient models to avoid unnecessary complexity. In this, similar models like LSTM, FTSA, and ADABU scores much lower than complex models like CNN and DFMM, which have very high values. Overall, the results highlights a trade-off. The voting regressor and ROBFTS are strong in predicting accuracy, while LSTM and FTSA offer better efficiency with less model complexity. Next, we have line feature contributions. Test sample is 0. The line plot explains how each feature influenced the model's prediction for test sample 0 by showing which variable pushed the prediction downwards, indicating red bars, or upwards, indicating the green bars. The strongest negativity contribution came from recent historical features such as lag 1, rolling mean 3, and lag 3, indicating that short-term past values or trend signaled or low expected outcomes. Additionally, smaller negative effects from rolling mean 7, total reservations, rolling standard 7, and lag 7 further pulled to predict down. In contrast, the features rolling standard 3 and weekday contributed positively, suggesting the higher short-term variability, and the specific day of the week slightly increased the model's output, with a minor upward effect also coming from the day feature. Overall, the combined influence of the strong negative lagged related features outweighed the smaller positive contributions, resulting in a lower final predicting for this sample. Next, we have feature contributions over time, SHAP. This SHAP heat map shows how each feature influenced the model prediction over time, with red areas indicating positive contributions and blue areas indicating negative contributions. The feature total reservation stands out as a dominant driver of predicting changes, displaying strong fluctuations across the timeline. Frequent red skips indicating periods where higher reservation counts increase predictions, while blue patches make movements where lower reservations values reduce them. In contrast, most other features including weather variables, calendar features, lag values, and rolling statistics remain relatively muted, contributing only small and stable effects. Occasionally, mid activities in features like lag 1, lag 2, and rolling standard 3 suggested periodic but much weaker influence. Overall, the heat map highlights that the model's behavior is largely shaped by variations in total reservations, with all the other features playing comparatively minor roles. And next we have SHAP mean summary plot. This indicates the total reservations, lag 1, rolling standard 7, rolling mean 7, lag 2, day, weekdays, lag 7, month, temperature, and precipitation. So next we have SHAP mean summary plot. This bar graph shows the mean absolute SHAP values for feature, indicating how much each one contributes to the model predictions on average. Total reservations overwhelmingly dominates the model output, meaning past reservation volume is by far the strongest predictors. The next most influential feature, lag 1, has a much smaller but still meaningful impact. while all remaining features rolling statistics, calendar variables, weather variables, and additional lags contributes only marginal by comparison. Overall, the model reveals highly on recent reservation history, with other temporal and environmental factors playing minimal roles. And next, we have SHAP value summary plot. This SHAP summary plot shows how each feature influences the model prediction with total reservations, with feature listed vertically by importance and SHAP values on the horizontal axis representing their positive or negative impact on the output. Each point corresponds to a single observation colored by the featured values. The feature total reservations has the strongest influence. High values totally push predictors up, while low values push them down. Short-term lag features and rolling window statistics also meaningfully affect predictions, showing that recent reservation patterns strongly shape the model's output. Calendar variables and weather factors have comparatively small effects clustering around zero SHAP values, meaning they contribute less to the model's final prediction. Then click on sign out. So, in the conclusion, this project showed that functional data analysis is an effective approach for predicting employees' presence by treating attendance patterns as continuous functions rather than isolated points. This method revealed clear trends, improved prediction accuracy, and provided deeper insights into daily and weekly behavior. Overall, FDA offers a powerful and interpretable way to support better scheduling, planning, and workforce management. So, this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.